Cool. All right, so what I think is what I'm gonna do for this walkthrough thing is write it up in Markdown. What was the example? Write up in Markdown and then just like go through all the necessary steps. I think that'll be fine. Okay. So starting with this first triangle, I think this... Oh, let me make sure my shortcuts are right. And it didn't work, so that's great. Oh, it's not this one. Let's check this. We get a triangle. That's great. Cool. Now, this is really straightforward, but I think that's all we need to get started with this. So I'll just write up how I want to go about this. Probably the definition of a shader. Question, what is a shader? Shader is a program that runs on a GPU. Next position, next position, next position. Eventually, I'm going to want to go through the pipeline. Or like the OpenGL pipeline. Like this, and here, let me just copy this from another source so I get it right. How do I find this? I think this involves rasterization. Is it here? Here? Surely. I feel like this isn't... Okay. Okay, here it is. So I'll get these vertices, convert those vertices to primitives, and the vertex shader. Oh, the vertex shader will move around those vertices. Then it'll generate the primitives, rasterize, shade, and fragment shader will shade them. Okay. Let's say vertices. Uh-oh, Ven's doing its thing again. I wonder if I can reset the terminal from here. I guess not. Yeah, it's still kind of freaking out. Is that any better? I think so. Nope. Hold on. Okay, so the pipeline vertices are passed to the fragment vertex shader. The vertex shader transforms the vertices. I'll say which will transform them. Or which then transforms them. It's just moving them around. Primitives are generated and passed, generated from the vertices. Primitives are generated and passed generated from the vertices and passed to they're generated and rasterized. So generated vertices and rasterized. You know what this uses raster I? Nope. Into pixels. I know it's not quite right to say the fragment shader acts on pixels. Fragments are slightly different from pixels. I wonder what it has to say on that. Vertex shader is executed for each vertex that is given into the rendering pipeline. That's actually a more precise way to say it. Say each vertex, or the vertex shader is executed on each vertex. Passed to OpenGL. The vertex shader transforms these vertices. Transforms the vertices. Maybe what I want to say is each vertex passed to OpenGL is run through the vertex shader. Is run through a vertex shader. Or passed to. Precise writing. Always a disaster. Is passed to vertex shader. The vertex shader transforms these vertices. Primitives are generated from the vertices and rasterized into pixels. Okay, so let me look into this rasterization. When the vertex shader is executed for each vertex, and the fragment shader is executed on each fragment. It says equal to pixel here, but I know it's not exactly pixels. That is generated after the vertex stage. Vertex would be called 3 times, one for each vertex. Fragment shader would be called 21 times, one for each fragment. So I want to get this difference right. Pixels and fragments. Just look through both of these. Demonstrate pixels and fragments. Very short, sweet, and to the point. Pixels are the smallest points on the display. Fragments are the smallest points on image data that is produced by OpenGL. Basically, it means exactly the same, but one pixel on the screen can be the product of more than one fragment, which is Z buffering, blending, etc. Also not be exactly correct. Use pixel when rendering to textures. Remember, this is just section terms. Directives use the term pixel. Okay, that makes sense. That's fair. The smallest points on image data that is produced by OpenGL. And then a pixel can be the product of more than one fragment from Z buffering, blending, anti-aliasing, things like this. Okay. And rasterized into fragments, which is, I'll say, roughly pixels. Let me make this into a list. Now I guess I can take out the periods. No, I'll leave in the periods. And rasterize into fragments. Then I guess I can take out the periods. No, I'll leave in the periods. And rasterize into fragments. Fragments are colored using, or colored by the fragment shader. Actually, maybe I can use the same phrasing that I used with the vertex. Hold on. If I can use the same phrasing, I think that'll make the idea a lot more salient. If I say, as I said before, each vertex passed to OpenGL is passed to a vertex shader. Okay. So I can say each fragment, rasterize into fragments. Each fragment created during rasterization. Rasterization is colored by the fragment shader. Geometry shaders, we don't talk about those. Okay, I think I want this in a different window. Close that. Close that. Close that. Was it example.md? Cool. So far, it's a vertex attached to a vertex shader. The vertex shader will transform them. Primitives are generated from the vertices. Rasterize and fragment. Each fragment is colored by the fragment shader. That's great. Okay, so I think for primitives, I'll put EG triangles, because that's the most common primitive. I think that'll make it a little bit clearer. Cool, so then with that, I think this code, you can almost understand all of it. So let me just see if I've gone through everything this code covers. Let me duplicate this. Alright, so this is the code, and I said each vertex passed to OpenGL is passed to a vertex shader, and I give the vertex shader here. Okay, so that makes sense. The vertex shader transforms these vertices. This basically isn't transforming them. Primitives are generated from the vertices and rasterized into fragments. Each fragment created during rasterization is colored by the fragment shader. So the fragment shader will have, it's very straightforward, just all red, and that's it. So the one thing I think I'll have to go over, normalized device coordinates to know why -1 here is important. So I'll do that. Okay. OpenGL. So I'll say OpenGL coordinates. I'll just call this normalized device coordinates. I think this is roughly OpenGL. How do I say this? The coordinate system that OpenGL uses is constrained. OpenGL uses, draws in. It's constrained, is constrained to a 2 by 2 by 2 cube with the x, y, and z axes ranging from -1 to +1. And I think that's mostly all that needs to be said about normalized device coordinates. From -1 to +1. And I think that's mostly all that needs to be said about normalized device coordinates. Yeah, at this point, the pipeline discards any vertices outside of a 2 by 2 by 2 cube with extents at this. Constrain 2 by 2 by 2 cube. Okay, yeah, so that's fine. So there's an example shader. Example, yeah, shader. Let's say Manim shader. I wonder if it's... Hold on, I should see if it's possible to render this using three-dimensional coordinates. Not totally sure if this will work. And I guess it didn't. Assignment of incompatible types. Let me see. GL position. Yeah, GL position must be a 4-dimensional thing. What I think I'll do for this example, though, is to make it 3-dimensional at first. So that I don't have to get into homogeneous coordinates right off the bat. So vec 3, and I'll just make this vec 4. A position and append a 1 like this. Okay, so this I think should run. Nope. Uh-oh. If I update the size. Great. So that's fine. Let me just update, or just copy it from here again. Okay, then I'll just walk through this. I'll say in the example shader above, the vertex shader simply outputs the same point passed to it. And then I'll just pull this out. There's probably a way to like label parts of code in Markdown. Maybe. But I don't know for sure. So I'll say, let's walk through the shader used above, starting with the vertex shader. Okay, here's the vertex shader. Then I can just write out this vertex shader. simply outputs the same point passed to it. The additional, I have to say something about the 1. The 1 appended to the point, or to the vertex, I'll say to the point, is... And here I don't know if I can get out of talking about homogeneous coordinates. And here I don't know if I can get out of talking about homogeneous coordinates. Which is a little unfortunate because my understanding of homogeneous coordinates is not the greatest. Let me see, if I go to this, let me just, if I change this to a 2, for example, still nothing happens. To a 3, 4. Oh, this is the color. Change this to a 2. Okay, so it has the effect of sort of zooming. But I don't think in practice you ever have this a different value than just 1. Let me see what I can find about it. OpenGL, if I just put in homogeneous coordinates. We've used 40 vectors matrix multiplication. Here to find where the 4th dimension is. Time to look at it's used for projective geometry. Find some time in the next couple of months to finish up the modern GL series. Projective geometry has an extra dimension called W in addition to X, Y, and Z dimensions. This brings things into projective space. And the coordinates are called homogeneous. They're not quaternions, thanks. So W, if you think of X and Y as the dimensions, then W is the distance from the projector to the screen. So then if you were to move things closer to the screen, that would correspond to making that value smaller, and that would bring it closer, make it look larger. And so I know that. It has to be the case that somewhere in between the vertex shader and the fragment shader, the homogeneous coordinates are converted into Cartesian. Yeah, so you take the W, you divide XYZ by W. Basically, how something from projective space is converted into Cartesian space. The 4th dimension W, usually unchanged. When using homogeneous coordinates in matrix transformation, W is set to 1 when you're converting a 3D coordinate into 4D. And it's usually still 1 after the transformation matrices are applied, at which point it can be converted back into a 3D coordinate by ignoring the W. So it seems like the only difference is really for projection matrices. So if I look at GL position, this is a vec4, which is the only reason that it needs to be a vec4 in OpenGL. Here. And so why is that the case? In the vertex, tessellation evaluation and geometry languages, a single global instance of the GL per vertex named block is available in its GL position member, and its GL position member is an output that receives the homogeneous vertex position. Hey, Evergram, what's going on? Okay, so I think the thing to say to make this as clear as possible is to say GL position receives a point in projective space. Homogeneous vertex in projective space. So I think what to write. The only one here on Friday night. Oh, well, I'm glad that just you're here. I think what to write. The only one here on Friday night. Oh, well, I'm glad that just you're here. Yeah, Twitch streaming is this sort of thing where I never really expect people to want to watch, but I'm super glad if they do. What I really hope to do is eventually... What other streams do you watch? That is a great question. Let me finish this section first, and I'll go into that in more depth. One appendage to the point is to convert the three-dimensional, is to convert the vertex into a homogeneous coordinate. I'll say vertices into homogeneous coordinates. More on this later, that's all I'll say. The one appended to the vertex I'll say appended to the... I'll say appended to position is to convert the vertices into homogeneous coordinates. More on this later. Okay, let's bring up my Twitch follows. I watch a fair amount of Destiny. He's kind of a controversial figure. Other than that, Dylan Burns is a political guy. I watch quite a lot of speedruns. This guy does Mario Kart 64 speedruns. And it turns out, if you're a relatively technical person, speedruns are also quite technical. A lot of the... Yes, this is like game-related stuff. A lot of the tricks that people end up employing involve actually the way in which the game manipulates memory or maps textures to things or whatever, detects movement. So this person's speedrunner. This is just a random stream I follow. I don't know. This person's semi-political. Have you heard of Summoning Salt? Of course I've heard of Summoning Salt. Yeah, he makes really good walkthroughs. Yeah, they train ML now to beat Mario. Yeah, that was really interesting. One of the things that I early on wanted to do with Manim was to make a video on ML, and I just wasn't able to do it. It was too annoying. So this was a programmer that I ended up rating and then ended up following. This person is a lawyer, so he talks about, he goes over like cases and stuff. This is a speedrunner. There's a programmer. They're doing around neural network vid. Similar to that, I wanted to do it over AlphaGo. Because AlphaGo, they just released their paper. It's not a secret how they managed to train their thing. Although I can't find it now. Is this it? But it wasn't even that long of a paper. Just looking for Google again. Yeah, kind of. 42 pages. Is this the same one? Oh, it was AlphaGo 0. Wait, is this one AlphaGo 0 or starting this, our new program AlphaGo? This is AlphaGo 0. But yeah, they publish just like all their methodology. It's not super long. Most of it, wait. Yeah, anyway. I read through this. What's the gist? They have a fairly large neural network, which was set randomly, actually. And then they had it play against other copies of itself. It's probably some huge thing, yeah. It's actually, if I remember right, it wasn't a huge one. It wasn't like impossible to do on your own. Like if you wanted to spend some money on Google Cloud or whatever. But then they had it play against itself and it just ended up getting insanely